Okay.
Oh, you
Okay.
started.
Uh, okay. Well, from the Bishop-Gromov theorem, we know that the volume ratio of the geodesic ball in the space with non-negative Ricci curvature with the Euclidean ball with the same radius is no greater than 1. And the equality holds if and only if the manifold is actually the Euclidean space. So this gives us some information that the Ricci curvature can help us to pinch the uh, local information together. Well, uh, in fact, the Bishop-Gromov theorem states that for complete manifold with no negative Ricci curvature, the sum of the ratio is no greater than 1. But as we know, when r tends to 0, this ratio is always 1. So the value 1 tells us no information about the manifold. So we restated the theorem in the asymptotic version, that is taking the limit as r tends to infinity. Okay, and combining with the positive scalar curvature, the ratio on the ratio could replace the order n on R to the n-2 order. This is because when for example we have the model space as S2 times R. Okay, let me write something. For example, S2 times R n-2 is our model space when we have positive scalar curvature, because we know S2 have the scalar curvature exactly 2. So the ratio, the order of R is n-2 on this ratio. And Gromov conjectures that this ratio should be finite. And if the hypothesis of non-negative Ricci curvature is replaced by the sectional curvature, then the conclusion is known to be true, and there is a sketched proof by Gromov in his paper, and you can find detailed proofs somewhere else. So, uh, uh, in we can restate the conjecture in an asymptotic version, that is taking the limit as r tends to infinity. Okay, the other hypotheses are the same. So, and the limit is evidently independent of p. So we are more concerned with the limit case since, as I mentioned before, this may give us more information about the manifold. Okay, there is an example. When in dimension 2, then Bonnet-Mears tells us the manifold is compact if we have positive Ricci curvature. Okay, in dimension 2, Ricci curvature and the scalar curvature is the same up to a scaling. So in dimension 2, the only manifold is topologically S2 with non-negative, with positive scalar curvature. And in general dimensions, we would conjecture that the cylinder S2 times n minus 2 is the manifold with the maximal volume growth rate. So, okay, and this is still unknown for general dimensions, whether or not this is actually the manifold with maximal volume growth ratio. And there are some results in dimension 3. Okay, this is clear in dimension 3. I will talk about this later. And for the three-dimensional case, it was proved by Munteanu and Wang in 2022 that there is a universal constant that such that the linear volume growth the linear volume growth ratio we know since the fact the order of R is 1, so we call this ratio the linear volume growth ratio. Okay, it's bounded about by universal constant. And I should mention that by a theorem of Yao, every no compact manifold with no negative Ricci curvature, we will have at least a linear volume growth ratio. So this R is the best. For example, we can replace R by log R. Log R is there is no such manifold with log R growth ratio and something else. And for higher dimensions, we don't know whether there will be something like R times log R. Okay, but for dimension 3, this is good. And later, there is a new method to prove the theorem using the mu bubble method and the Cheeger-Colding sum of splitting by Chodosh, Chao, and Stryker. They prove the same theorem in using mu bubbles diameter estimate. And based on the previous work, okay, Wang Yipeng also proved the result for the no-asymptotic version, because we see this is sup, not the limited sup. Okay, he proved that the ratio is also bounded from by a constant. But this constant is unknown whether it's sharp. It's unknown what's the sharp upper bound for this kind non-asymptotic version. And we want to know the asymptotic version. Is it what's the optimal upper bound for this asymptotic volume growth ratio, and if whether or not the model space S2 times R minus 2, the cylinder is a manifold with maximal volume growth ratio. And the answer is actually yes. The cylinder is it's yes in dimension 3. Okay, in dimension 3, S2 times R has a maximal volume growth ratio. This is the theorem in 2024. Wei Guodong, Xu Guoyi, and I, we proved the sharp version for the asymptotic volume growth ratio in dimension 3. And we show that the optimal value 8 pi is attained if and only if it is a cylinder S2 times R. And we should mention that an independent work by Wang Xiantao and Liu Shuai also recovers this result using, using harmonic functions. And we use essentially different methods because we use the mu bubble method and we use the harmonic functions. And the theorem is actually in 2 parts. The first part is when M has only one end. By one end, I mean the connected component of M. For example, M is something like this. It has only one connected component outside the compact set. For example, a compact set K. Outside the compact set K, the manifold has only one connected component, and we call this is one end. And if it has 2 connected components, then we call it 2 end. Okay, when it has one end, the volume ratio is no greater than 4 pi. And each value between 0 to 4 pi can be attained, and 0 cannot be attained because we have a theorem of Yale. Okay, for each value in 0 to 4 pi, we can construct a manifold with such volume growth ratio. And as we can see, there are at least two kinds of manifolds, so there is no rigidity for this case. And in dimension, and this is a figure for the one in the case that is a half cylinder, and with each slice a 2-dimensional sphere, and with scale f, because we construct the manifold by using a Y product, and the scaling is f. Okay, and the second part is when M has at least 2 ends, then it's from the Gromov, Cheeger-Gromov's splitting theorem that it must split into a cylinder. So in this case, we could deduce the volume ratio is no greater than 8 pi. And each value can also be attained by using the cylinders. And only when 8 pi is attained, there is rigidity, that is a cylinder. and the other values have no rigidity because you could replace this sphere by making a small perturbation, and it also have scale curvature greater than 2. So let me draw a picture that is the model space in the 2n case or more n case. Okay, we can also ask a generalized question instead of the volume growth ratio. Instead, we can integrate the scale curvature in the geodesic ball and ask whether or not this ratio have asymptotic ratio uniformly bounded from above, and this is conjectured by Yao. And note that we have no hypothesis on the scalar curvature here because we are integrating it in the geodesic ball. And this is evidently a generalization of Gromov's conjecture because if R have a strictly positive lower bound, then this conjecture implies Gromov's conjecture. And there are some, the conjecture is still unknown even for dimension 3, and there are some partial results. For example, Zhu Bo in 2022 proved the theorem with the extra hypothesis on the manifold have a pole. By a pole, we mean that the exponential map from a point is globally defined diffeomorphism on the whole tangent plane. So in this case, he showed the ratio is actually bounded from above. And this result is improved by Guoyi in 2023 that the ratio is actually equality to 8 pi and minus the volume ratio for the 3-order volume ratio for the geodesic ball. Okay, so this not only gives us the upper bound 8 pi, and it also gives us the rigidity information for every manifold because this is an equality, not an inequality. Okay, and if we I should mention that the hypothesis is also with a pole. So if we don't have a pole, there is a recent result by Wang and Munteanu that if the scalar curvature is bounded between two positive constants, then the limit sub is also bounded by 8 pi. So this gives us confidence to the original conjecture by Yao should be true because the positive constant can be taken arbitrarily. So although we can arbitrarily take the bounds, the upper bound for the limit is always 8 pi. So this gives us confidence for the original conjecture to be true. Okay, and for higher dimensions, the answer is still unknown. And not only Gromov's conjecture, but also Yao's conjecture are still unknown. And in 2022, Zhu Bo proved the conjecture with an extra requirement on the injective radius lower bound. That is, if we have inject radius strictly positive, the inject radius is the biggest value of the radius such that the exponential map is always a diffeomorphism on the geodesic ball with radius r. Not the geodesic ball, the ball in the tangent plane. Okay, with the extra hypothesis, Zhu Bo proved the theorem, the conjecture in general dimensions. And the non-asymptotic version, before we are considering about the limit sense conjecture, and the non-asymptotic version is still unknown, and the sharp version is also unknown for dimension 3. And there are some partial results by Wang Jingming, Xie Zhang, and Zhu Bo, Zhu Xingyu. They prove that with if we replace the sub by inf, then the hypothesis, then the conjecture is actually true.
Hey, Shuai, I have to mention out, I think the injective radius, that one, there is a gap. That's why finally we write this paper. I think there is a gap. I have to mention now. Okay.
Okay.
In the future,
Okay,
don't
thank
talk
you.
about it.
Okay, thank you.
Yeah. Yeah, that's why we write this one with Xinyu and others too.
Okay, thank you.
Yeah.
Okay, it's also reasonable to ask because our model manifold is S2 times R, the S2 times R n minus 2. So if we look far away from this manifold, we will look at it. It looks like just this part. So it's natural to ask whether every n-dimensional manifold with positive scale curvature is actually n minus 2 dimension in the large scale. And the formal definition is as follows. That is a macroscopic dimension. It's defined to the smallest integer that such that there is a continuous map from the manifold to a simplex with dimension p, such that each fiber have uniformly bounded diameter. For example, if we consider S2 times R, we can map R into a unit interval by using arctangent and by scaling and something else. And you can see each fiber is S2, so it has finite diameter. So the macroscopic dimension of this manifold is actually 1. And for n minus 2, it's the same. The dimension is n minus 2. Okay, you can replace everything to n minus 2. So Gromov made the following connector that the macro dimension of n manifold with positive scale curvature will be no greater than n minus 2. And there are some partial results, but the problem is still widely open. Okay, okay, I'll talk about why dimension 3 is so special. Because we have a diameter estimate for two-dimensional manifold. But let's begin with the elementary theorem that's well known, the Bonnet-Mears. If a complete manifold has Ricci curvature bounded from below, then the manifold is compact and the diameter optimal upper bound is attained if and only if the manifold is actually the round sphere. So there are some extensions. One of the essential thing in the Milbaum method and something in the minimal surface is the following lemma by Shuai Zhang. It's only valid for two-dimensional submanifold. There is no submanifold in the lemma, but we will only use the lemma for two-dimensional submanifolds. Okay, it states that for two-dimensional surface, if we have the a positive function such that the Laplacian adding the reciprocal scalar curvature. Okay, in dimension 2, that's why it only works for dimension 2. That's it, because the scale curvature, the sectional curvature, and the scalar curvature is the same after scaling. So if the inequality holds, then we have the diameter upper bound. And there is recently another proof by Chodosh and Chao using the Milbaum method. And it's curious that we will naturally ask whether or not this diameter upper bound is sharp or not. And it's curious that it's sharp and it's not obtained by the round sphere, and we will talk about it later. I will discuss the relation between it and the Bonnet-Mears, because if we have u a constant function, then the Laplacian term is omitted, and we have Ricci curvature bounded from below by a positive constant. So that from the Bonnet-Mears, okay, if k is equal to 1. So from the Bonnet-Mears, we have the diameter upper bound. And as we know, Bonnet-Mears theorem, in Bonnet-Mears theorem, the diameter upper bound is only attained when the optimal upper bound is attained only when the manifold is a round sphere. but in the previous lemma, the diameter is not attained by the round sphere. And we'll talk about that later. But before that, let me first introduce why we need this lemma. This is because it appears, the hypothesis, it appears in the second variation in minimal surface or the mu bubble surfaces. Okay, for example, in minimal surface, the second variation looks like this. So this is the Laplacian term, and this is the scalar curvature term. So we can use the previous lemma to the stable minimal surfaces. And the mu bubble surfaces are the same. And there are some other terms, so we need a slight change of the previous lemma, but the idea is the same. Okay, and for example, Shuai in their paper using the previous lemma to prove the stable minimal surface have a uniform diameter of bound if the ambient manifold has scalar curvature positive. And the lemma also have a variety of usages, but I don't have enough time to introduce them. So let me just briefly introduce that we will need the lemma to estimate the diameter of a bound in the mu bubble. Yeah, for the mu bubble. And okay. So as we talked before, the previous lemma, the diameter of a bound is actually sharp. And it's curious that the diameter of a bound is not realized by any surface. It is attained by a sequence of surfaces that converge into a one-dimensional segment that and its diameter converges to the optimal upper bound. And this is a figure. It looks like a cylinder and with two caps. So you need to carefully choose the cap so that it is a smooth manifold, and you need to choose the smooth function in the definition. Okay, all in all, this is an example for the previous lemma that it is actually sharp in the asymptotic in the limited sense. And it's curious that the sphere is not the best. And also, we are able to give one example for the Shuai theorem on the complete stable minimum surface, that the bound given by Shuai is actually sharp, and there is a sequence of complete three manifolds with each have a complete stable minimum surface and with diameter limit the optimal bound. Okay, and I still have time to sketch the proof of our volume growth ratio theorem. Okay, I will sketch a proof for our volume growth ratio theorem. First of all, if M has at least two ends, then it necessarily contains a geodesic line. And then from Cheeger-Gromov splitting theorem, the manifold is asymmetric to a cylinder. That is, it splits to a manifold N with positive Ricci curvature because R contributes nothing to the scalar curvature. So N must have positive scalar curvature. For example, R strictly positive. So if N is a two-dimensional surface with positive scalar curvature, then it has positive Ricci curvature and sectional curvature, and then by Bonnet-Mears and the Bishop-Gromov's volume comparison, we have the manifold N is compact and its volume is bounded from above by 4 pi. And a direct computation will show the volume growth ratio is greater than 8 pi. And when M has only one end, we will prove instead of 8 pi, we will prove it is actually no greater than 4 pi because if the model space is a cylinder. Okay, the two end case is a cylinder with two ends. So a geodesic ball will have two direction which it gets bigger in two directions. And if it's it has one end, then it can only get big in one direction. And in this part will contribute nothing to the limited sense, in the limited sense, to the volume growth ratio. So the idea for the one end case is that we first cut the whole manifold into a sequence of cylindrical regions. That is, okay, we are not actually doing this for M. In fact, we are doing this for the universal cover of M. So that is simply connected, and we can ensure that after each cut, our cylindrical region is connected. Otherwise, it would be bad. And we are not actually cutting, okay, we are cutting along the geodesic spheres. For example, we take the connected component outside the geodesic ball. For example, EK is something like this. This is EK plus 1. Okay, and this is E, and this is EK. Okay, and this is EK. So the difference between EK and EK plus 1 is the cylindrical region we will estimate. Okay, so when we cut the manifold into cylindrical regions, we can estimate the area, okay, the volume for each region by using the curvature formula. Firstly, we are cutting along the geodesic spheres, so it's also cutting by using, so it's equivalent to cutting using the geodesic distance from the point P we have fixed. So if we are doing using curvature formula, we are doing with the distance function. So the Jacobian or the distance function will be 1. So we only need to know the height and the area of each slice. And the okay, the height part of the estimate is actually the most difficult part, because in this part we use the Cheeger-Gromov's almost splitting theorem. Cheeger-Colding is almost a splitting theorem, and we use the mu bubble surfaces because if we want to estimate the height, we first use the Cheeger-Colding's almost splitting theorem to guarantee it looks like somehow a cylinder, and the diameter of the cylinder is controlled by the distance from the two boundary parts. Okay, I should mention that the distance from the two boundary part of NK is L, and K is a positive constant. So the distance from the two boundary part is L, but the manifold may have arms. Okay, for example, this is some arm of NK. It will be very large if we don't have some control. So the main idea is to control the diameter of the arm. So we first use Cheeger-Colding's almost splitting theorem to first reduce the question into some cylinder. And the cylinder of the diameter of the cylinder can be controlled by the distance between the boundary parts, that is L. And the arm part is controlled by the slice, the diameter of the slice. And the diameter of the slice is controlled by the mu bubble surfaces, the diameter for the mu bubble surfaces. So that's why the proof only works in dimension 3. That is, the mu bubble surface have dimension 2. So we can use the previous diameter bound for mu bubble surface in dimension 2. And the area part of the slice has the upper bound. Okay, I should mention that the previous upper bound for the height is not exactly L plus C. It contains some other terms, but they are all small compared with L, because we will take L to be infinity. So there are some other terms I omitted for simplicity. Okay, and the area estimate for each slice of NK. Each slice is a geodesic sphere. So each slice of the area of each slice is controlled by using the mu bubble surface. We have some control on the area of mu bubble surface, and then we use the same philosophy as the Bishop-Gromov comparison theorem. That is, like in Bishop-Gromov, we are comparing the geodesic spheres with the Euclidean geodesic spheres. So we have the volume bound for the geodesic spheres in manifolds. And in our case, we are comparing the area of the geodesic sphere with the mu bubble surface. So we have the control for the area of each slice. And this is very important because the upper bound is in some sense sharp. This 4 pi is sharp in some sense, so that we could get the sharp upper bound for the original volume growth ratio. And if we don't do this rigorously, we can just integrate using Carrera formula and just adding together all the volumes of each cylindrical region NK, and we get the following expression for the upper bound of the geodesic ball. And if we calculate this integral, the sum of the integral will get okay. When we just it's just a direct calculation, we find this will tend to 4 pi times something gets smaller and smaller as L tends to infinity. So the conclusion then follows if we let L tend to infinity. And there are some details I omitted, but I believe the philosophy is here. That is, we cut it into cylindrical regions and estimate the height and the area of each slice. Okay, that's all. Thank you for your attention, and I'm sorry for the no sound. And is there any questions?
Any questions? Okay, I think everyone understood you. Okay, no worries. Okay, since there is no question, yeah, let's end this talk. Okay. Thank you, Shuai.
Yeah, thank you for your attention.
I think our, okay, let me